So hello everyone, welcome to EduMoon. Today we are going to discuss about the overview of digital logic exam, digital logic design exam, as you're having for tomorrow's exam. Now I invite Samuel sir for opening the syllabus right now. After the syllabus, Samuel sir will be coming and he'll be helping you in getting good marks for tomorrow's exam. So all the best, guys. I welcome Samuel sir. Sir, welcome.
Yeah, hello. Good afternoon, everyone. So tomorrow we're having the exam on digital logic design subject.
Sir, welcome.
So let us have the syllabus on the screen first of all. Because can you put the syllabus?
Yes, sir.
So
Syllabus
actually
is on the screen, sir.
we used to have 7 chapters in the original syllabus. Now it is reduced to 70%. So we have 5 chapters. So from the 5 chapters again the number of questions is same. That is we need to answer 4 essay answers out of 7 and the remaining are 2 marks. So we can guess that the important chapters are third chapter and the fourth chapter. So which covers the lot of syllabus. Basically, the fourth chapter itself is the chapter which covers almost 30% of the original syllabus. So it takes almost 1 to 3 chapters is almost equal to the syllabus of the fourth chapter. I guess you can zoom in because you can zoom in the syllabus because we noted everything on the screen. So just zoom in the syllabus. So coming to first chapter, second chapter, third chapter, and fourth chapter. And also we have the fifth chapter for the examination, which is sequential circuits. So those who want to start this subject, actually you need to start from the first chapter itself because even though you have 1 week time or 1 hour time or 1 minute time, this subject we need to follow from the first topic itself, right? Which we start with the basic binary numbers, number-based conversions, and octal and hexadecimal numbers. What is the relation between octal and hexadecimal numbers? Then one more important concept in the first chapter is complements. So what is the use of complements? How can we use complements for subtraction? And then finally the chapter concludes with the binary logic. There we actually study only the basic 3 binary logic operations, which are and or not. Okay, which are and or not. So if there are any questions regarding the number based conversions or how to convert an octal to hexadecimal directly or how to use a complement, we already have the PPT. For each chapter individually, we have PPT for the 4 chapters. So for the first chapter, Vikas, can you share the PPT for the first chapter? You can use your live chat box so that you can have questions regarding the first chapter. This is the model paper you can see. Okay, we'll go with the first chapter. So these are the topics briefly in the first chapter. What is the decimal system? What is a binary number? How different numbers are being converted from one base to another base. So in this 1.3, 1.4, and 1.5 are important key points to note. And we'll be sharing this PDF in the Gmail group. You can download that and have some questions over there. So number based conversions is an important topic from the first chapter. So as the syllabus is reduced to 70%, we can expect a question from the first chapter for 14 marks. And basically these are very small topics. So number based conversion is something which we are interested about. So converting a number from one base to another base, like decimal to another base, and some base to decimal, or else some decimal, or else directly converting a base 5 number to base 7, whatever, different bases, and also a fractional part in that. In number based conversion, if you are expecting a question, it can be a fractional part, like convert a number called 23.58 to binary. So decimal points and fractional points, that is also an important thing. You can go through that. And next one is octal and hexadecimal relation. So any number which we need to convert from one base to another base, if there is not decimal number, we need to convert to decimal first. That is, if there is a number to be converted from base x to base y, first of all we need to convert that base x number to decimal, then from decimal to base y. But there is a relation between octal and hexadecimal. Without converting that octal or hexadecimal to decimal number, we can directly convert to the other base. That is the relation we see in octal and hexadecimal. And coming to complements, you can go through the next slides in that PDF, because There are some examples given in this PDF about binary numbers, how the numbers are converted from one base to another base, and complements. Go to the next slides because to complements. Yeah, this is all introduction about digital systems, and next we come with binary numbers, how the binary numbers are converted to decimal, vice versa. Then converting the numbers from other base to some other base. So this is the basic things we study. What is the number system and what are the different bases? And these are the examples of conversion. You can see there are several examples here. And then there is a relation between this one, octal and hexadecimal. So then we go with these complements. So most of you are confused about complements. I have come with some questions from the students when I'm teaching this one. What is the complement of a number? So basically remember, if a number is of base r, we have two complements, r's complement and r minus 1's complement. So obviously a decimal number has 10's complement and 9's complement. There doesn't exist any 1's and 2's complement for a decimal number, right? And we use these complements for subtracting of two numbers. If at all you people doesn't know anything about a complement or else how to subtract, perform subtraction using complement, you can take it as an example. Uh, if you had a questions, you can put it in the live chat regarding this one. And also this PDF will be provided in the group. You can go with that. Right. So after this complements, the other important topic, or else which we conclude this chapter, is actually about binary logics. Right. The basic three binary logic operations, and from that we'll be starting our second chapter actually. So this chapter concludes only with converting different numbers, and there are some codes. Go to the next slide because these are some example problems given from the textbook itself. And if you at all you have the textbook, you can practice some problems within the short time you have. Right. So in the next slide, you can see the codes, binary codes like gray code, XS3, BCD, 8421, all these codes. So just having a glance of this will be useful for the 2 marks or the simple questions you can answer, because the first chapter doesn't contain a very big answers actually. But regarding our syllabus, you can expect a question from the first chapter. Right? If there are any questions regarding the first chapter, you can use the live chat and you can have the solution for that. Or else then the second chapter, it starts on the Boolean algebra. So 2, 3, 4 are very much linked. So without understanding second chapter, you cannot go to the third and fourth ones. So mostly in the second chapter, because can you open the PDF for the second chapter, digital logic design for the second chapter. There also in the starting we can see the Boolean algebra rules. How to simplify a Boolean expression, given Boolean expression using the postulates. So different laws are there. It is very important to understand those laws like distributive law, associative law, and one important law is De Morgan's law, which is very much familiar with all of you, and of course it is important coming to the exam point of view. So in the next slide, you can find what are the Boolean algebra rules and what are the different laws we use. So commutative law, associative law, all these laws may be useful for the 2 marks questions and also for the essay questions, because if you want to prove any law using a truth table, right, generally you'll be asked for the three variables which are directly from the textbook problems. In the next slides, you can find some questions regarding what is then algebra and what are the different laws that are given in Boolean algebra. So these slides consist of those laws. And one important law you can expect is De Morgan's law. So how to prove the De Morgan law? And using these Boolean algebraic rules, we will be simplifying the expressions, the Boolean expressions. And next we go with the so these are the on the screen you can see the basic Boolean algebra rules. And then we come with functions. So if a function contains an expression with some variables like three variables or four variables, we try to minimize that into minimum number of literals so that it will be easy to implement using a logical gates, that is nothing but a circuit diagram. So in this chapter, what is asked is generally a function is given, you are asked to write the truth table or else you are asked to implement that using the basic gates. And one important thing is about standard form and canonical form in this chapter. Second chapter, you have the canonical form, that is SOP and POS. We simply call it as SOP and POS, sum of products and product of sums, where SOP means we have min terms or n terms or product terms, all are same. So where we write a binary value 000 as x dash y dash z dash. You can see it in the next slides. You can go to the next slides where you find the table for the min terms and the max terms. So on the screen you can see how the function is implemented using a circuit diagram and the truth table. That's a truth table and the function diagram. So go to the next slides because where we find that table for min terms and max terms. Yeah, from here actually we start with the min terms and max terms. And this is the table. You should remember this very well because each min term is given the designation of M0, M0, which is given in small letters there, and max terms are written with the capital letters. So any function, if it is represented in min terms, it can be converted again into max terms because they are complement to each other. So generally in this chapter, the question you can expect is if the function is given, either you are asked to implement that with logic gates, or you are asked to write the truth table for that, or else prove the equivalence of two functions, and then finally converting an expression from sum of products to product of sums or vice versa. So that is what we have in this second chapter. And also the logic gates. The last topic in the second chapter is logic gates, right? In the basically first chapter we study only the basic logic operations that are and or not, but here you can see the other operations which are derived from the basic operations like NAND, NOR, XOR, XNOR, etc. So using those gates we can implement these functions. That is, we can write the circuit diagram for the functions. So this is how the conversion between the canonical forms is. You can see it on the slide. So however, we'll provide this entire PDF in the Edgeman channel. You can have a glance of that. But now that if you have any doubts regarding these topics, you can put it in the live chat. And you can expect the question 14 marks directly from the first chapter and the second chapter. Right. So if you're thorough with 1, 2, 3, and 4, because now that syllabus is reduced to only 5 chapters, definitely there should be two essay questions from any of the chapters. So the first and second chapters are basically uh, comparatively smaller than the fourth and third chapter. So maximum we expect a question only for 14 marks. Apart from the 2 marks, only one essay from the first chapter. You can go thoroughly with the previous question papers where hardly 7 marks is from the first chapter. But here, since the syllabus is reduced, so but those who are having the supply exam, I guess definitely again 3 and 4 chapters are very important. And mostly don't think you have much questions in 1 and 2 chapters because they are only the basics, right? So what all we study in the second chapter are what is a Boolean expression, how to represent that in the table, how to draw the circuit diagram for that expression, and how to minimize that, and finally how to convert an expression from one canonical form to the other canonical form. So these are the 5 topics you can go through, right? And in the next slide, in the last slide of this one, I guess we have given the logic gates, the table for the logic gates. Let us go to the slides further. You can see the logic operations, all the logic 6 or 7 logic operations and their respective gates and their truth tables. This is the table for, yeah, this one. This is the table which shows all the possible gates and their tables. Important questions for yeah, even for supplementary, third and fourth chapters are most important because you can only follow from each chapter. You cannot jump over the chapters in this subject particularly, like what we did for the other chapters. Like in data structures, even you don't know stacks and queues, you can jump over to sortings or graph theory trees. But here that is not the situation. So always you start from the first chapter, right? So you only if you understand the first chapter, you can go to second, then third, then fourth, and five. So for supplementary students also, you can go with the 1, 2, 3, 4 chapters. There only can cover almost 5 essay questions. because fourth chapter actually contains a lot of topics. Right. So we'll see quickly what we can see in the third chapter, because one and two chapters are really simple to understand. And if there are any questions regarding three and four, you better ask in this. Important questions for supply or even regular. The K maps is very very important. Yeah, chapter three. This is chapter four, because go to the chapter three. Yeah, this is chapter three. So gate level minimization. Here, the very very important, most important thing is the Carnot map, or else simply we call it as a K map. You can definitely uh, expect a question from the Carnot map without any doubt, because that is the most important way to simplify that. So basically, we start with two variables and three variables and four variables. So since this is asked for an essay answer, I guess, so it will be asked for minimum three variables or four variables. So of course we had five variable and six variable, but we rarely use them. So first of all, if you understand two variable, practice more problems in three variable and four variable, and also okay, Nand and or implementation. That is end of this in this chapter. We'll explain that on the board. We had a whiteboard here. So if there are any doubts in the KMAP, first we discuss that and we go with that NAND and NOR. And also in KMAPs, the another small important concept is don't care condition. How the don't care condition is actually implemented. In the further slides, you can see that don't care condition. Because go to the slides. I mean, in this PDF, go to the other slides where you find the KMAPs for don't care condition. We had given some very good examples in this topic. And someone is asking a question about, sorry, can we expect a question about HDL? Yeah, hardware description language. Very simple one. We have one HDL code in this PDF also. We'll explain that. So this is the Karnaga for two variables. We can directly go with the three variable. I guess most of you know what is a two variable map. So go to third variable or else fourth variable map. So when you draw these K maps, make sure that the order or else the map structure is correct, because I see the common mistakes when they write the numbers inside the KMAPs with min terms, that is 0, 1, 2, 3 and all. So go to the next slide. This is two variable. Two variable, I guess no one has a doubt about that. But in three variable, you can see that is M0, M1, M3 and then M2. That is because they follow the gray code there, right? Even in the four variable map structure, because go to the four variable map, because I guess most of them doesn't have any doubt in three variable. So we'll explain that NAND and NOR on the board. Yeah, next slide. Next, fourth one. And in K maps also there may be multiple answers, because the mapping can be done in different ways. The only thing is you can either yeah, next one, go forward for two more slides. You will find an expression there. Yeah, this is a structure of four variable, and in the next slide you can find the example. Next slide. Yeah, this one. So you can see that function A is given. So function F is given. Yeah, come back because you have gone forward. So how to simplify this one? And sigma is given. You can map in different ways. And finally, the don't care condition. So most common mistakes what I observe here is the structure of this four variable map. You can check that the numbers from 0, 1, 2, 3, the 15 will be at the third row and third column. Okay. So make sure that before answering in a hurry, please make sure that you can write it correctly. The structure of the map, because it follows a gray code. Mostly I see the people who answer, they give the numbers in a actual manner what you follow, like 0 to 15. So 0 start from the first block and 15 ends at the last block. But here in KMap, that 15 is at third row, third column. I guess you know the difference of that. So someone has asked the questions for which chapter good marks for scoring. Yeah, third and fourth chapter. Definitely three and four chapters you have very important concepts. So we go with someone has asked the question about NAND and NOR implementation. So I'll write it on the board, NAND and NOR. So why are they are useful? Because if you can see the board, is it visible or not? Let me know.
It is visible, sir. It is visible.
Yeah, you can present it on the screen. We'll
Yes,
enter that
yeah,
on NAND.
everyone is seeing now. Yes, sir, yes, sir.
So NAND and NOR are called universal gates because using these gates you can implement any other gate. So basically, so if you have only NAND or NOR gates, you can create any circuit. So if at all you want to implement a NOT gate first, a NOT gate using NAND gate. So I'm writing it on the board here. A NOT gate on the NAND gate using NAND gate. So you know the NAND gate symbol. This is the symbol of NAND gate. If at all the inputs are A, B, you get A dot B whole dash. Right? That is what is NAND gate. But if you give the same input A to both the inputs of a NAND gate, it will be A dot A whole dash, which is nothing but A dash, right? Which is almost equivalent to A dash. So this is how we implement a NOT gate using NAND gate. Then we go with AND gate, an AND gate using NAND gate again. So again, we take an AND gate. So the output of this one, if it is AB, the output is again AB whole dash. So if you want to remove this complement here, so again use the same not operation what you have done previously here. So this gives you AB, right? This is NAND operation. Again, you performed a NOT here using the same logic what we have done here. So we get AB there. So this is AND gate using a NAND gate. Finally, OR gate using a NAND gate. So first of all, we take one input A, we complement that using a NAND gate, and we take B. Again, we can complement that using a NAND gate. So we use these two, again the whole complement. So actually this is A dash here and this is B dash here. Now this is A dash dot B dash whole dash. So using the De Morgan's law here, that is why we call De Morgan's law very important. So using the De Morgan's law here, this will generate A plus B because A dot B whole dash is A dash dot B A dash plus B dash according to De Morgan's law. So already we had a complement here for AB, so we get A plus B here, right? So actually in the board my writing is not so clear, but I think you can write it very well in the examination using however you don't have the marks for handwriting or using a blue pen or black pen, but just represent it neatly, that's it. So now we go with the NOR implementation here, the NOR gate implementation. So again, first we implement NOT gate using NOR gate. So basically NOR gate, again NOR gate looks like this one. So when this is AB, so this will be A plus B whole dash. So again, using the same logic, if we give the same input to NOR gate, that is A plus A. So A plus A is also A. So this will give us A dash, right? That will give us A dash. Now coming to the next one, AND gate again. So AND gate using NOR gate. So this is A dash, same what we had done previously. And this is B dash. Again, perform the NOR operation between these two. So you get A dot B, again using that same De Morgan's law. And finally OR gate. OR gate using NOR gate. So this is, if these are AB, this will be A plus B whole dash. So to remove this complement, again we perform the NOT what we have done previously. So this will be A plus B. So now you can actually observe here the important concept, that is then AND logic for NAND is same as OR logic for NOR, and the OR logic for NAND is same as AND logic for NOR. So you can see this structure is same, these two, but however this is same equal. Here AND using NOR is same as OR using NAND. Okay, so these two are actually same, right? So someone is explaining the question there. In chat box, we had a question. Maximum, how many questions can we expect from 3 and 4 chapters? If it is a supplementary exam, I guess definitely 28 marks plus the other 2 marks, or else at least 2.5 essays sometimes from 3 and 4 chapters. That is 35 plus 2 or 3 short answers also. So expect at least 32 to 40 marks from only 3 and 4 chapters. Definitely minimum 32 to 40 marks from, and maybe even more than that. Even more than that for the regular students, because however you have only 5 chapters. So if at all you can take the 2 essays, minimum 3 essays from these 2 chapters, it is around 42 marks plus 2 marks. So almost nearly 50 marks from 3 and 4 chapters for the regular students, and for supply at least 35 to 40 marks. Right. Any other doubts regarding this? So this is not almost done here, because we have just shown what is the implementation here. Later, actually, we try to implement the circuit diagrams using only NAND gate. That is what the question is given. This is just the example. So here I'll show you how to draw a circuit diagram using only NAND or NOR. So if you have that expression over there, right? So I think you can see it on the board. So if at all we have taken an expression x dash plus yz, right? This is a function f. Okay. So if I want to draw the circuit diagram for this one, when there are 3 inputs x, y, and z, so this is x dash, this is yz. So we are using an AND gate here. So AND gate, and so we want to make this one as an OR operation. So this is finally f. Now this is the original circuit what you draw for using the basic gates. But if at all you are asked to implement that using only NAND gate, so what we ask here. So replace these gates with the NAND gates what we have seen there previously, right? So we can use that, like if this is x, so we use that NAND gate operation, so you get x dash here. So this is the NAND operation for the NOT gate, already you have seen that. And AND operation for NAND is this one, right? AND operation for NAND is this one, this is the AND operation. And finally the OR operation. So OR operation using NAND, we get the same circuit like this. And finally with these two will be again perform NAND. So this is what we get f. So I'll make it clear for you. This is the NOT gate implementation. This is the AND gate implementation. And this is the OR gate implementation, just what we have seen earlier. We can rewind it and we can see. But here still we can simplify this circuit, because you can see here there is a negation of negation. So a dash whole dash will be equal to a. So using that involution logic, we can simplify these gates. And again here x dash and again x. So this is again negation of negation. So we can simplify this circuit by drawing like this. If this is x, you can eliminate these two gates and also these two gates. So after eliminating that, so this will be like only two gates, because we already eliminated 4 gates there. So we can implement that function using only 2 NAND gates. Other than using 3 basic gates, we can implement that using only 2 NAND gates. So this is how we can implement a NAND logic, and also similarly a NOR logic. So someone has a question, explain about magnitude comparator. Yeah, that is in the 4th chapter. We are still dealing with the 3rd chapter. If there are no questions from the 3rd chapter, I can go with the 4th one. And there is the other guy who is asking question. Solve the Boolean expression AB dash plus A dash B into A plus P. Explain this. So the first one is XOR, the next one is OR operation. So what is that? You want to express that, or so if you multiply that, okay, I'll show it on the screen. If you multiply that, I guess you can pause the video whenever you want, so that because we are switching with the doubts. If you haven't noted, you can pause that and note down. So again, I'm coming back to the screen original board. Right here, the question is asked is this one: a dash b plus ab dash to a plus b. So if you multiply this, this is a dash b into a plus a dash bb, right? You multiply these two and again these two. So this will be a b dash a plus a b dash b. So again here a dash and a, this will be 0. So this is b into b, that is a, this is a dash b plus again this is a b dash. So this is again 0. So you are left out with again a plus circle b. Okay, that is so simple, right? So basically you need to have that Boolean draw. So someone asked the question, Pathraju. Yeah, this is the solution. Finally, you get again a plus circle b itself. It is on the screen. Prime implicants of K-map, actually it's not given in our syllabus because we explained only the simplification of K-maps, and there is also a Twinkie other map method. We doesn't have that in the syllabus. So generally prime implicants is used by EC people where they design for VHDL and etc. HDL. HDL, one student asked a question from HDL. Someone like Nicola Duvuri. Okay, roll number 41 from IT. Right. So here HDL is we'll take a small circuit here and we can write that. Yeah, you can use any technique, whatever. Just now we have used that, right? Backtracking. Yeah, you can use that. But on the last day of the exam preparation, I guess if you have done a mistake over there, it will be completely a blunder mistake. So that is why we are not going to shortcuts now, right? So HDL, I'll take a small example for the HDL, right? If this is a circuit, if it has three inputs, let us assume that it has three inputs and assume that this is the circuit. Just now we have seen that, right? And let this be D, right? If this is the circuit given, how to write the circuit for this one? How to write HDL code for this one is hardware description language. We simply write describe this circuit in a simple language. That's what is called hardware description language. Now let me name these gates like this is G1, this is G2, this is G3. If there are more number of gates, you can name them. And I'll name this circuit as something like a device, right? So now how to forward like this is same like you write a C function like sum, right? A comma B, and you write so many steps here in declaration and all. Same likewise here, we declare this circuit. So assume that I named this circuit like some module, right? In this, the parameters we write as a function. So here, what are the parameters are A, B, C, and D. So same thing, what we write is the inputs and the outputs. Next, after here, general in C function also we represent what is the variable, what is the data type of the variable, like is it integer or character or floating type. Same thing we write here. We write here like inputs. Inputs are ABC, right? And output is D. So from this we cannot tell what is the input, and maybe input AB or input or CD is output. But that is why we declare here what are the inputs and outputs. Then we have something called wire. I'll tell you what is wire in a short while. So next one, first of all, we go with the first gate. What is this gate? G1, right? That is of NOT gate. So first one we write is NOT gate G1, right? So first we write the output, then the input. So the input for this NOT gate is only one input, that is A. So always gates have only one input, one output. There can be any number of inputs, but definitely NOT gate has only one input, right? So A is the input, and what is the output? So from this circuit diagram, all the lines are either input or output, but there are few lines which are not neither input nor output, but they are connecting internally the gates. Like you can see this gate, this wire. Okay, this is called a wire because this is the output of this NOT gate and going as an input to this OR gate. So we call this as a wire W1. So I declare that as W1 there. And again this one. This line is an output of G2 and going as an input to G3. So I'll write it as W2, right? So here the NOT gate output is W1, right? Next one is AND gate. So that is AND gate, that is G2. So the output of this AND gate is actually the wire W2, right? And the inputs are B and C. So actually we should write that wire 2 first because this is the output. B and C are the inputs. Now finally the OR gate G3. So this the output is D, the inputs are W1 and W2. So we concluded everything. So that is why all the lines except the outputs and the inputs, all the internal connections, we call them as wires. So we completed everything. So we can simply say it as AND module. Most repeated question in the HDL is they will be giving directly circuit, either half adder, full adder, or a subtractor. Okay, and you are asked to write the HDL code for directly full adder. Then you need to draw the full adder circuit, and then you can write the HDL code. There is someone, sir, once check the question. Hold dash. Where is it? Hold dash. The question is not given as a hold dash. Yeah, okay. There's a hold dash. Then it will be a NOR operation. You can simplify that using NOR operation. That will be XNOR. Even the XNOR, you can multiply that to finally get A dash B dash plus AB multiplied by AB. So you will be left out with only A plus B, I guess. Important question. That is what we are discussing here. Pothraju, when you have that hold dash, you can take it as an XNOR multiplied by A plus B, right? Even if it is AB dash plus A dash B, when you perform a complement to that, you get A dash B dash plus AB, and you are multiplying that with A plus B. So finally, you are left out with again A plus B, right? So are there any doubts in this KMAMs or don't care conditions? Then we go with it, or else fourth chapter, that is magnitude comparator from combinational circuits. For solving NAND and NOR logic, yeah, you can use that. If you are very confident, you can use it, or else in a conventional way, you can go stepwise so that you never get a mistake. So if there are no doubts in this one, you can see the PDF of fourth chapter, chapter 4, the very much important topics. In the third chapter, we can go with that K-maps, both for SOP, POS, and don't care conditions, right? And finally, the NAND NOR implementation, that is very important, and then HDL. HDL is widely used by ECE people because they had a lab, even VHDL lab. Another example in K-maps. You want an example in K-maps? Because can you show that PDF on the screen where we have that example of K-map? So I'll tell you what are the common mistakes they do in a K-map are. So yeah, this is the K-map. Okay, I'll explain that on the board as someone asked that. I think you can see some question on the board because just switch to my whiteboard on the screen. Because just switch to my whiteboard on the screen. Yeah, I think you can see some expression out there. Sigma 0, 1, 5, 7, 8, 11, 13, 15. right? So if you want to draw a KMap for this one, so this is how a KMap looks like with four variables. So generally the common mistakes what the students should do is, I'll tell you here. So once you draw the map here, right, you will mark ABCD here, that is right. So 0, 0, 0, 1. Here it is 1, 1 and 1, 0. Mostly they swap this, they write in the general binary order what we see. Actually, that is 1, 0 here and 1, 1 here. So please be sure that you write these correctly. Until that, you don't go to the marking of that. If you want, you can write this min terms here. There is 0, 1 here, next 2 comes here, then 3 here, 4 here, 5 here, 6 here, and 7 here. Mostly the people who have followed the three variable up to here, they do it very correctly. But mostly they write 8 here, but 8 is here. That is the worst common mistake I can see mostly people, and 10 here and 11 here, right? And next 12 here, 13 here, 14 here, and 15 here. I took some random numbers. I don't know what will be the answer for this one. So we'll just mark that on the uh, map. So what are given is 0, 1, 5, 7, 8, 11, 13, and 15. Right. These are the given values here. So what can you do here is you can actually first identify a quad here. So identification of quad is very important. Then you can either pair this one, right, with this one, and these two is a the let well use another color here. This is also a pair there, right? And here finally this one is there. You can pair this one with this one or this one. Both are correct. Okay, so kmap doesn't have a unique answer. You might get different answer, but that is okay. So actually from this squared, actually what is changing is, you can observe here, a is constant and a is changing and b is constant 1, and in this it is d is constant. So from the quad, actually a and c are eliminated. You can see when you perform a quad, when you observe a quad there, two variables will be eliminated, and in this pair definitely one variable is eliminated, that is a again. So it is b dash, c dash, d dash from this pair, right? So this is the first quad, this is first second pair, and if you take this one as a third one, the third term will be in this one. Again b is changing here, it is a, c, and d, right? And finally this one you can either pair with this one or this one. So if I do it in this way, the fourth term, so that will be a bar, b bar, c bar, right? But if you do it with this way, it will be something else, that is a bar, c bar, d. Both are correct. Either you write this one or a bar, c bar, d, right? Either this one or this one, right? This one when you pair in this way, and this one when you pair in this way. No need to do both. You do either one. That is enough. So that is how K-maps are very, very important, right? It doesn't take much time or else many papers to write, but the thing is write them concentratedly and thoroughly check twice or thrice whether you have given the correct answer or not. Because a small change of one can change your answer, right? So the concept is simple and also very interesting. The only thing is you do it carefully and just check once after you completed that. Theory question on HDL, I think you don't have any theory questions. See, HDL, our importance is very less. As for CSC people, HDL is not so important because we're not interested in designing circuits later in our VHDL lab. But for EC people, if at all there is any person from EC, they will understand the importance of HDL because they had a subject and they had a lab also, which we call as VHDL lab. Is there a chance of a five variable map? Maybe they may ask you what is a five variable map. So five variable map, it is very difficult to draw the five variable map. Just you can draw the mirror image of this one on the other side. Uh, but also you can draw two four variable maps, leaving the first variable a. You can write for B, C, D, E. And for one map, you can put a equal to 0. The other map, you can put a equal to 1. Right? Five variable maps. So in the next chapter, we go with the fourth chapter. Because can you present the fourth chapter topics so that I guess in fourth chapter most of you will have the questions. So we thought of having a 1 hour session here. So the fourth chapter topics are combinational circuit. It starts from combinational circuit, designing and analyzing the combinational circuits. Then we go with the adder and subtractor. So there are a lot many internal topics in adder and subtract like half adder, full adder, subtractors, binary adder. Then we go with the decimal adder, and binary adder subtractor is the one which is very important. Then binary multiplier and magnitude comparator. So one of the students asked the doubt from magnitude comparator. So again, in these circuits like binary adder, magnitude comparator, and decoders, etc., we may have different sizes like a 4-bit magnitude comparator, 4-bit binary adder, right? And even in decoders, there are different sizes like 2 by 4, 3 by 8, etc. So we go with the magnitude comparator now. So what does the magnitude comparator does is, you can switch onto the board again. I think you can see the board. So generally in magnitude comparator, now this is a combination circuit which will take two numbers, two binary numbers, and simply writing it as MC, and there are possibly three outputs. Now assume that this is A and this is B. So the three outputs are A is equal to B, A greater than B, or A less than B. Right, these are the possible three outputs there. Right. So I'm taking the 3-bit, or else you can take it as a 4-bit. Mostly 4 bits are asked. So we are assuming that A is 4-bit, like assume that A is A3, A2, A1, and A0. 4 bits in A, and B also having 4 bits, B3, B2, B1, and B0. Right. So when these two inputs are given, these two numbers are given as input, this comparator, this device will actually output whether if they are equal, they are greater than s. What are the relation between them? So what is the magnitude relation between them? So only these three possibilities, right? If the both numbers are same, this output will be 1, these two will be 0. And if A is greater than B, the second output will be 1, the 1 and 3 will be 0. And if B is greater than A, then the third output will be 1, 1 and 2 will be 0. So how will you going to compare this one? So first one, for example, if A and B are equal, what we do is assume that both should be equal. So in this case, for example, if you take 0, 1, 1, 0 for both A and B, these are equal. That is, each bit, that is A0 should be equal to B0, A1 should be equal to B1, A2 should be equal to B2, and A3 should be equal to B3. That is, these two should be either 0 or both should be either 1. Again, these two should be either 0 or both should be 1. So here we write a function called x0, which is A0, B0, or A0 dash, B0 dash. Right. So when will be x not equal to 1? If either both these are 1 or both these are 0. Right. If both a naught and b naught are 1, or if both a naught and b naught are 0, we have that x not equal to 0, or x not equal to 1. So similarly, if you write for all xi, right, for all the bits, assume that xi equal to ai bi plus ai dash bi dash. Right. Then a equal to b, the equation for a equal to b can be given as, right, all the x will be equal to 1. So x3 should be 1 and x2 should be 1 and x1 should be 1 and x0 should be 1. So when all these are equal to 1, then a is equal to b. That's the equation for a equal to b. You can find the circuit in the textbook. I will share that. And a greater than b. How can you tell that a is greater than b? Very simple. For example, in binary numbers, right? If this is 0, 1, and this is 1, 0, we already know this is 7 and this is 8. Even though this has 3 ones in this one, this is less than this one, because in the MSB bit, we have 1 here and we have a 0 here. So similarly, if A3 is 1 and B3 is 0, right? If A3 is 1, you can write it here. If A3 is 1 and B3 is 0, you can simply tell that A3 is always greater, because the magnitude of 1 is higher, because that is again 2 power 3, right? So if A3 is 1 and B3 is 0. So we write A3 B3 dash, because if this is 1 and this is B3 is 0, B3 dash will be 1. Right? We can conclude that A is greater than B. Or, for example, assume that the first two bits are same. The first two bits are same. If the first two bits are same, what we do is we compare the second bit. Right? So if first two bits are same, x3 will be 1. If x3, then we compare the second bit, that is A2 B2 dash. Right? And next, if the first two bits are same, then you write x3 x2. If the first two bits are same, then you compare a1 b1 dash. If the first bit, second bit, and the third bit are same, then you compare a0 and b0 dash. So that will be the equation for a is greater than b. Right? Similarly, if a is less than b, you can simply write the same expression. You can write the dash to a instead of b. So this will be a3 dash b3 x3 into a2 dash b2. Sorry, this is a, or x3 x2 a1 dash b1 x3 x2 x1 a0 dash b0. Right, that is the equation. So someone has a question here. So summation sigma 0134 for 4 variables, convert to SOP form and equivalent logic circuit steps. Converted to SOP form, should I minimize the expression or not? If at all it is asked for converting, I mean just conversion, you can write it in the sigma terms. That is sigma 0134 is given for 4 variables, but actually that is enough for 3 variables. Okay, if it asks for 4 variables, always A will be complemented. Always A has a complement over there, right? So if this is clear, you can, I'll simply erase the board, right? Those are dots, you can pause it or else I'll play again. So someone has doubt here, that is sigma 0134. So generally here expression will be given like W, X, Y, Z, whatever, or A, B, C, D. So let us take W, X, Y, Z. So when you write this one, it's 0, you can write it as W bar, X bar, Y bar, Z bar. So this is 0 is nothing but M0 plus M1 plus M3 plus M4. So summation, it is simply given as sigma. Sigma is nothing but SOP. And 1 is W bar, X bar, Y bar, Z. 3 is W bar, X bar, Y, Z. 4 is W bar, X, Y bar, Z bar. If at all it is asked for simplification, then you can go with simplification, or else generally you write in the SOP form like that. So the question is actually not clear. Is it for 4 variables? Then already the sigma is given there, right? If it is asked for POS, okay. If the question is asked for POS, I can extend this question. So obviously the pi is the elements which are not in this one. So you can write 2, 5, 6, and 7 if it is only for 3 variables. If not, you can write the remaining variables up to 15, that is 8 to so on up to 15 also. Right, that is the equivalent term. Remember that they're complement to each other. That is, for example, if 3 variables, I'll write that one also. If 3 variables are there, A, B, C, is this is sigma 1, 3, 5, and 7. This is equal to pi of 2, 3, 4, and 6. Right, and f dash will be equal to the complement of that again is equal to sigma of 2, 3, 5, 4, 6, right, and pi of 0, 1, 5, 7. You know, this is the function f is this one, the equivalent POS is this one, and if and the f dash is this one, and its equivalent pi is this one. uh, Fourth unit after the magnitude comparator, the important, very important, the two concepts are decoders and multiplexers. They are very much important. And decoders, there are different sizes, I guess, 2 by 4, 3 by 8, etc. And sometimes you are asked to implement a 3 by 8 decoder using 2 by 4 decoder, right? Or else a multiplexer with a smaller size to larger size. That is, implement a 4 by 1 multiplexer using 2 by 1, or else a 16 by multiplexer using a 4 by 1. Such questions will be repeated so frequently. You can see in the exercise problems, because I think you can share that textbook which was given to you, the PDF of the textbook. In that, directly go with the exercise problems. I guess maybe the page number 185. There some exercise problems are there for decoders. You can also implement a full adder using decoder, and or else an expression using a decoder. Similarly, you can implement address using multiplexer and address using the other circuits, and a function using a multiplexer. Yeah, you can zoom it a bit, make it full screen, or else it is actually blurred up. Maybe those who have the textbook, you can follow that. Mostly exercise problems are very important from the fourth chapter. So those who feel it comfortable with the third and fourth, mostly complete all the topics from 4 and 3. If you are very much confident about 4 and 3, then you can go with the fifth chapter, that is flip flops and other. Unless you are asked to minimize the function in order to minimize. Yeah, you can see some questions over here. There are expressions given, and you are asked to implement them with using decoder, right? Even in K-map, sometimes the expressions are not given in terms of min terms. Rather, they are given in terms of an expression.
Sir,
You need to
are you
answer them.
asking page number 185, sir?
Page number 185, I guess. The exercise
This is
problems
the
in the
one.
fourth chapter. Yeah, that one. You can zoom it a bit so that it's not clear on the screen actually. Is there any other questions from the fourth chapter? Like
4.3.
adders, subtractors, decoders,
Yeah,
multiplexers.
what HCL we have, sir, here? Combinational logic behavior models.
Yeah, designing a combinational circuit is very important topic. Or else in the PPT you have that questions how to design. They will be explained. The design of that circuit is explained orally. Like you are explained with that circuit has three inputs and two outputs. The first output is equal to one if this is the case, and so on. It is explained in general terms. Then you need to uh, formulate table first from the given description. So every combinational circuit has generally those four properties, which are block diagram, truth table, equations, and circuit diagram. So block diagram generally shows you the what are the inputs and outputs and their names, and then we go with the table. If I can format the table from the given description, you can find the equation using the K-map, and finally after the equation you can give the circuit diagram. So that is the general method you do in the designing a combinational circuit. Or else in the notes you have different combinational circuits. Go with the exercise problems. Chapter 3 and 4 important questions. Again, someone has the same question as we had told you earlier. K-map for 4 variable, 3 variable, don't care conditions, Nand in our implementation in third chapter. And fourth chapter, decoders, multiplexers are very important. Then adders and magnitude comparator. Most of these decimal adders or else binary multiplier are not so frequently asked, but decoders, multiplexers, and adder subtractors are very important. Go with the PDF because I mean the chapter wise. the PDF of individual chapter, that is chapter 4.
Yes, sir.
And if there are no questions from this one, you can go to the fifth one, which is flip flops, etc. Yeah, this is the first chapter. Go with the fourth one.
Fourth one, sir. This is chapter 4.
Yeah, fourth one. This is chapter 1,
Chapter 4, sir. What I'm showing right now is chapter 4.
chapter
Combinational
4.
circuits and analysis procedure.
Yeah, this one. This is the common circuit, and this in this the important topics you can see it on the screen. The last two decoders, multiplexers, and encoders. Mostly it is in the textbook for only 1 or 2 pages because it is very simple to understand. If you understand decoders, just it is the reverse of a decoder operation. And in that, priority encoder is another important topic. So you can go with that priority encoder. It might be asked for 2 marks or even for an essay many times. So if there are no doubts in this fourth chapter, I'll tell you the important topics in the fifth chapter, which are actually in the textbook. So if there are no doubts in this, we can go with the fifth chapter. In fifth chapter, you can go with the uh, okay. In the fourth chapter, there is an example for design. Someone asked for design procedure. Because go with the fourth chapter. I mean, in the slides, there we have a design procedure.
Yes,
We'll
sir.
explain the design procedure there.
Yeah. So design procedure.
In the fourth
So is
chapter,
the
you can go with
screen
the
visible?
design procedure.
Yes, sir.
Yeah, it's yeah. Next one, and the next one. Yeah, this is the design procedure we have on the screen. Right. So designing a combination circuit, if the definition is given formally, you need to first format the table. First of all, in the block diagram, you can see the number of inputs and outputs. Then we go with the formation of the table, basing on that statements given. And for the outputs, you can find the equation of the outputs using a K-map with the respective inputs. And once you get the equations, you can draw the circuit diagram. So as an example, you have a code conversion example here. One is given as BCD to XS3, and similarly gray to binary, binary to gray. The other examples are there. So for all the design questions, designing of a combinational circuit, you can follow the same thing. If there are no doubts in fourth chapter, we'll move with the fifth one. So mostly those who have started the preparation, I can go with 3 and 4 a lot. So we'll be providing these PPTs in the PDFs in the Edgemon channel. Right, we can go with the textbook fifth chapter, sequential circuits. So sequential circuit starts with the introduction of a flip flop. So we need to be thorough with the circuit diagrams for the flip flops, 4 flip flops, JK, D, T, and SR. So the first one is SR actually. So after analyzing the circuits for those 4 flip flops and their tables, that is the characteristic table and the equations, the characteristic equation of each flip flop, you will be asked to design any sequential circuit provided you will be given either a state diagram or as the state equations. Mostly the state equations will be given in terms of A of t plus 1 and B of t plus 1. So you can see it on the screen about the sequential circuit. Immediately they'll follow with what is a latch, what is a flip flop, right? Then you go with the design, right? Again here, if the equations are given, first you format the state table, right? And also the circuit from the state table. Finally, the state diagram. State diagram is something new which we don't find that in a combinational circuit. But mostly students doesn't answer that question from the fifth chapter, because if you are thorough with the four chapters, then you can go with the fifth one. My suggestion is, if you are very much thorough with the four chapters, you can ignore the fifth chapter, those who are regular students. And for the supplementary students, you can go with the last topic, that is memories. In memories, the topic PLA, PL are quite easier compared to the other topics like counters and registers. If there are no more questions from the fourth chapter and fifth chapter, we can conclude that. We will send some important questions in the Edgemin channel also. And these PDFs, in these PDFs also, in some slides, we had some questions, important questions that are discussed. I can start with the first chapter, and there is a one question paper, which is a model paper. Because can I show that question paper on the screen? So in this question paper, you can see that this is the old question paper. Here in the first question,
So this is a question paper, sir. Sir, 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 your voice is not audible.
yeah, is it audible now?
Yes, sir. Now we can hear you.
Yeah, is a question. I mean, someone is asking about the PPTs of these chapters. I think you can provide them. So I'm just
Yes, sir.
reading out the questions here. The first one is, you can zoom in the question paper there. For the 2 marks question, a number-based conversion is asked. That is also in fractional part. And the second question is binary codes. Binary codes include BCD, XS3, gray code, etc. And what do you mean by register? So for current regular students, this topic is not there. But register means a group of flip-flops or else a collection of flip-flops. An n-bit register contains n flip-flops there, right? And next convert given into the SOP. So already POC is given, you need to convert into SOP. And next one is, what is a ripple counter? That is a spelling mistake there. Ripple counter or else asynchronous counter, both are same. So those who are attempting for supply, you can go with that, because it is same as asynchronous counters, where the clock pulse is different for every flip-flop. Synchronous counter means all the flip-flops have the same clock pulse. Asynchronous counters or else ripple counters, they have different clock pulse for each flip-flop. Next, what is a latch? So latch is also a storage device. Each latch is capable of storing 1 bit of information there. And list different types of memories. Types of memories, you can go with semiconductor memories, RAM, ROM, EEPROM, and maybe again the ROM variants also there. What you study for EDC there and or else microprocessor, the ROM variants, PROM, EEPROM, right, etc. So next one, GBT is what is the memory, list out different. Okay, that is done. So in the essay questions, you can see that in the first question, second question is from the first chapter, access 3 code converter and the logic gates. Okay, types of logic gates with their diagrams and truth tables that we provided in the PDF of the first chapter itself. There are almost six logic gates, etc. And or not, XOR, XNOR, right, NAND and NOR. So you can see the next question from the third one, that is NAND NOR logic, right? NAND and logic there. So expression is given, you need to draw the circuit with NAND NAND. And the next one is simplify using K maps. So here it is asked for only 7 marks, but generally for tomorrow you can expect a 14 marks question from K maps. So next one is what is a multiplexer and what is a demultiplexer, right? So here there is a direct question. It is not asked about any size. So multiplexer is a circuit which has two power and inputs and only one output and possibly n selection lines. So these selection lines are used to direct one of the inputs as an output. So demultiplexer does the actually the reverse of that. So which is same as a decoder with an enable input, right? So in the next question you are asked about 4 by 2 encoder. So which is also reverse of a decoder here. So difference between a latch and a flip flop. The clock pulse is the difference. So generally latch has doesn't have any clock pulse to trigger the next state, but latches have the uh, enable input there. So next one is a combinational circuit that has four inputs and four outputs. So from that you can derive the block diagram. Four inputs you name them as ABCD. Four outputs you can name them as WXYZ. And the output is generated in two components. So you can format the table immediately, right? Then you use the K-map to simplify that and finally get the equation. So in this fifth question particularly, maybe you can guess that the 5A is only for 4 marks and 5B is for 10 marks because that's a big question, right? And explain different types of registers. This is also from registers topic. BCD counter. So in counters, those are going with counters. You can have a bit counters or mod counters. So BCD is nothing but mod 10 counter, which is same as mod 10 counter. You'll have states from 0 to 9 only. And here it is explained as synchronous. So there are two types, asynchronous and synchronous. So here they asked you synchronous counter with BCD, that is from 0 to 9 states, right? And the seventh question is given with a state diagram. So the numbers are given there. You can assign the binary values for those numbers. You can draw the state table from that. You can derive the equations and then draw the state diagram or a circuit diagram. And the next one is also a circuit diagram. I mean state diagram given. Again, you need to assign the values for each state, format the state table, get the state equations, and draw this circuit diagram. And the last one is from the semiconductor memories, like which is asked for 2 marks. And those who are trying the eighth chapter in the textbook, PAL and PLA, both are very easy and very simple to understand, but definitely get a question from them. So, is there any doubt in the fifth chapter? Those who feel that this is very difficult, then definitely you should answer the third and fourth chapters very well, because as far as I concerned, that definitely will going to get more marks from those two chapters. You practice more access problems from the textbook from those two chapters. So is there we'll be providing the PPTs or else the PDFs of these chapters in the group. If there are no more questions, we can stop the session now and we can have your preparation.
So, guys, if you have any doubts, you can ask now. Sir is available.
Is there any question from the topics?
Thank you so much, sir, for sparing your valuable time and teaching all the juniors for tomorrow's exam. I hope it's very informative to everyone, and all the very best, guys. As sir said, all the PPTs will be presented at you within 10 minutes right now. So all the best for exams, and thank you so much, sir, for spending your valuable time with us.
And
Thank you.
still, we have some questions. We are, shall we continue or not? Some question is there. You can
So
see it in the
the
chat
question
box.
is encoder and decoder.
First, you understand the decoder concept, the concept of decoder well, because you can go with that PDF of fourth chapter. We have the decoder slide. So, decoder is a combinational circuit
Yes,
which has n inputs and maximum of 2 per n outputs, right? So, there will be different sizes 2 by 4, 3 by 8, 4 by 16, and so on. That is n inputs. Then we can have maximum of 2 per n outputs, and this will generate the binary information. That is, whatever the input combination, the respective binary output is set to 1, right? If it is 2 by 4, we get 4 combinations of the input like 0
sir.
0 0 1.
Decoder chapter is on
Fourth
screen,
chapter.
sir. Yes, sir. Decoder is on.
Yeah, we couldn't see that on the screen. Are you sure it is on the screen?
Yes, sir. It is now.
Yeah, go to the next slide then. We can see the diagram directly.
Yes, sir.
This is okay, that is actually 3 by 8 circuit diagram, but you need to have the 2 by 4 first. I think 2 by 4 diagram is there. Or else you can switch to the camera so that I'll explain that on the board as someone asked
Sure,
that.
sir. Yes.
Is it visible on the board?
Yes, sir,
Is the
it's
board
visible now.
visible? Okay, switch to that. So decoder, so generally the block diagram is it has some n inputs and maximum of 2 power n outputs. So we call it as n cross 2 power n. So as an example, we can take a 2 by 4 decoder. So 2 by 4 decoder means this decoder has 2 inputs and 4 outputs. We simply call it a 2 by 4 decoder. Assume that these inputs are A and B, right? So the outputs are D0, D1, D2, and D3, right? So the truth table is very simple. You can see A, B are the inputs, D0, D1, D2, D3 are the outputs. So when this is 0, 0, D0 will be 1, the remaining will be zeros. And this is 0, 1, D1 will be 1, the remaining are zeros. This is 1, 0, D2 will be 1, the remaining is zeros. And finally, when these two are 1, D3 is 1. So you can see the diagonally we will be having ones. So for any combination of the input, only one of the outputs will be equal to 1. And if you write the function for this one, it is almost equal to the minterms only. You can see D naught is 1 when A B are 0 0. That is A bar B bar. So this is A bar B. This is A B bar. And finally this is A B. Right? So following this, we have the circuit diagram also. So the circuit diagram is as follows. We have two inputs A and B and the negation. So we have four outputs for using AND gate. So the first one will be A dash B dash. The second one will be A dash B. The third one will be A B dash. And the fourth one will be A B. This is A and B. So we have D0, D1, D2, and D3 respectively. So similarly, you can have 3 by 8 with 3 inputs and 8 outputs, 4 by 16, etc. Right? Now coming to encoders, encoder is just the reverse of this one. Right? Encoders are nothing but the just reverse of this one. It has 2 power n inputs and n outputs. Right? So in the PDF, you can follow that. We have simply encoder diagram. So you can have 4 by 2 or else 8 by 3 circuits. So encoder, we can simply have the diagram also. So it has 2 power n inputs and this time n outputs. These are n. This is 2 power n cross n. So example, we can take a 4 by 2 encoder. Just you can reverse the circuit diagram there, right? So the inputs will be E0, E1, E2, E3, and the outputs let us assume that AB. Okay, this time around, only one input is kept as 1, right? The other inputs are 0. Then the respective binary value is given. So just change the inputs and outputs vice versa, like this one, right? So here input side will be having all ones, I mean diagonally ones, right? So you can get the equation of A and B and the circuit. So there is a question, there is a small modification in encoder, that is, what if two inputs are kept 1, right? So for example, if E0 and also E2 are 1, what should be the output? Which of the binary value should be there? So that concept is in priority encoder. We call it as priority encoder. This is also important concept. So then there we take as priority to the highest number. Like when E0 is 1 and all other are zeros, then you get 0, 0. But when E1 is 1, then you don't care about E0. So we put an X there. And when E2 is 1, we are not bothered about E1 and E0. So in that diagram for priority encoder, in the lower triangle, you get all don't care conditions. That is what priority encoder is, right? So if you understand decoder, encoder is very simple, and there is small modification in encoder, that is priority encoder. So I guess we have answered some questions for the students. If there are no doubts, we can conclude the session and
There are no more doubts, sir. I think we are good to conclude. So thank you so much, sir, for everything, sir. And guys, all the PPTs which sir showed right now will be displayed in the Eduman website in few minutes. So you don't need to worry because major comments, everything are from everyone are telling to keep PPTs. So don't worry, and all the best for your exam. And thank you so much, sir, for giving you this time. Thank you, guys, and all the best, everyone.
yeah, thank you.